Hello, my name is Giulio Ruffini. I'm a theoretical physicist working at Neuroelectrics in Barcelona and also at the Barcelona Computational Foundation. And it's a real pleasure here to present my talk about the algorithmic worldview, an algorithmic Platonic perspective as part of the wonderful symposium organized by Michael. So thank you for the invitation, and here we go. So my talk is organized in different parts. The first one is philosophy and mathematics. I will then talk about the algorithmic agent, then about more specifically, more detail about modeling, compression, and symmetry, then about the relationship between about the algorithmic framework of the agent and first-person structure experience, and then about time. And I will close with some reflections on algorithmic ethics and values. So I won't go a lot in detail here, but just to mention that there is a long list of historical research and figures and thinkers related to what I'm talking about here, starting from digital physics and computation, algorithmic information theory, and in particular cosmograph complexity, predictive coding, the free energy principle and active inference, cybernetics, agents and control, neurophenomenology. And I would say that what's new here is kind of a synthesis based on algorithmic information theory, trying to link the mathematics of such agents and the first-person structure experience, and the implications of this in computational neuroscience and neuropsychiatry, and also in AI. The questions I will touch on and the questions that interest me are very much shared with many of you, I'm sure, and they include what is consciousness, what is reality, why is mathematics so powerful in science, what is time, who is the famous observer in quantum mechanics, and who am I at the end, and who am AI at some stage. Maybe some AI systems will inquire about this. And I think it's fascinating that today, thanks to the rapid evolution of artificial intelligence, we found ourselves talking to actually mathematics. When you have a discussion with ChatGPT or with Gemini, and you're discussing a topic or trying to figure out some research question or some debugging problem in your computer, you're actually talking to mathematics. From the physics point of view, this is not so surprising because even other human beings are physical systems which are at the end governed by mathematics, but it makes it very much, it highlights how much we're relying on mathematics now. And also we see in the literature pointers to the idea that there are some shared Platonic structure, shared mathematical structure across different AI systems, LLMs, and other such systems. And I will try to convince you in this talk that this Platonic representation, a hypothesis of this Platonic representation is not a coincidence, and it's actually due to the fact that all these models are trying to capture structure in the world and actually achieving it. And simplicity in the search for these models is part of the guiding theme. From the philosophical point of view, the philosophical backbone of what I'll be talking about starts from the idea that there is structural experience that any one of us has. So we have experience, which is kind of this base layer of experience that does not necessarily have to be attached to a lot of structure per se. And in fact, we can define it as all the intersection of all possible experiences that we may have. But then there is structure on it, and so this defines the idea of structure experience, which is the phenomenal structure of consciousness encompassing the spatial, temporal, and conceptual organization of our experience. So it's not only experience, but it has structure in it. And thanks to this structure in experience, we are actually able to report it in some cases to ourselves and to others. We can report it to ourselves as a form of dialogues or memories, and we can also transmit this to other sentient beings that are able to decode our messages. So here what this theory is trying to do is to develop a first-person theory, a theory about structure experience and how that relates to mathematics. The postulate of the theory is essentially that there is experience. This is not something that the theory or the framework tries to demonstrate. It just takes it as granted as the only thing that we actually need not prove because we experience it, we are aware of it, and it is in fact the only thing that we can be certain of. But then we will shift the focus on structure experience. What is endowing structure to our experiences? And here's a picture to differentiate the two. pure experience, which has no structure, no relations, but is the base layer. And then there is structure around it, which consists of relations and simple mathematical structures that capture relationships between things. So the modern Descartes might say, I think, therefore I have structure experience, or I exist, therefore I have structure experience. But then continue to there is structure experience, therefore there is pure experience, and also mathematics. And this is the thread that I will follow in the talk. So starting from structure experience, I talk about pure experience and mathematics, and the fact that they are both part, philosophically, we can say that they are part of some common base. And this is a form of dual aspect monism or cosmic idealism. Just a few words about this. So experience without mathematics is ineffable. There is no report, no agent, no world to talk about. And conversely, mathematics without experience is empty. There is no intrinsic what it's like. So the same base of reality would have both an experiential and a structural phase. So there is experience and there is a logical structure on top of it, a mathematical structure. And this is what they call the unicum, as the primitive element, philosophical backbone of what I talk about. I'm not the first one to do this. Other people in the past have done, and in particular, and very timely for this symposium, Pythagoras also talked about the idea that reality is the combination of experience and mathematics, and the rest was kind of it's just an imagination, an illusion that we have. So since we're talking about mathematics so much, let's try to mathematics. So we can think of mathematics as the science of structure, and this is actually the definition in Encyclopedia Britannica. I would like to think of mathematics as some kind of logical tiling, logical system with some axioms and rules that only fits one way and constructs a complex structure, relational structure. Now, if we think of the universe as being composed, being defined by this logical tiling, then we may ask, where does computation arise? It's an interesting question, and I would like to just suggest that because I think computation is not fundamental, but it's kind of a derived, something that could be derived from the theory. But one key aspect of computation is that it requires steps. So computation requires the execution of a program or procedure in steps, and these steps are essentially the idea of time. And the question arises, well, where is this time in a logical tiling, which is supposed to be the mathematical universe? And the idea is that maybe you can recover that through the procedure that is sometimes used in general relativity, about talking about time slicing. So the idea here is that you can take a logical tiling and slice it in some particular way in order so that you're actually able to locally at least reproduce the next layer in the tiling via some procedure. Even though the tiling is a 3D object, or it's not a 3D object, sorry, it's a logical, very complex network, but you can slice it in some way and recover some rules for evolution. I'm talking about this because computation is basically what I'm going to be using from now on, so I'm going to be abandoning the tiling, this mathematical Platonical realm, and go into computation. And computation, I think, as I mentioned, is not so fundamental. It really goes back to some other more abstract thing, which is the tiling. But in order to visualize this, I offer you this image, which is a Penrose tiling, which is a tiling made of a few pieces that only fit in certain ways and can give rise to very complex structures, as an analogy, as a metaphor for the mathematical tiling I am talking about, the logical tiling I'm talking about before. And you can also see here some white lines which try to portray the idea that there is some slicing of this tiling, which allows you to go from one slice to the next through a procedure, through an algorithm, basically. On the right, you have the same kind of idea using Wang tiles, which are shown to be universal. So, anyways, this is just a metaphor to try to convince you that it may be useful to think about things in this way. Another word that I use in the talk is computation, and I like to define it because it confuses the discussion many times. when people have different ideas about what computation means. By computation, I don't mean using a laptop or something like this. I'm talking about really Turing machines. And when I talk about a physical system computing, I am referring to the idea that physical systems and dynamics can be really made to appear as computation or to embody computation. So for example, we can say that a physical system like my laptop is actually simulating or computing what another system does. For example, I don't know, a brain, a computational brain that is trying to emulate. When there is an isomorphism between the two. So that in the laptop, if you coarse grain, a laptop is a very complex system with a bunch of atoms and all that. But if you coarse grain it, if you average out certain aspects of it, and you end up taking the meaning of values in pixels, for example, as a coarse grain of the laptop, you can actually simulate or in mathematical terms build an isomorphism between that and what happens perhaps in the EEG of a subject, which is another physical system which we also coarse grain in such a way. And the same thing at the end you can do with this more abstract sense with a Turing machine. So both the abstract and the physical systems that I'm talking about here can be made to emulate one another via isomorphisms and coarse graining. So this is the idea of computation. This is very much inspired in a paper by Wolpert and Corbel this year. So now let's talk about the algorithmic agent. So the algorithmic agent, the idea starts from the following. There are in this algorithmic soup, in this algorithmic system, which we may think of as cellular automaton, for example, as depicted in this picture, there are patterns that presumably, under some conditions, will persist after computational eons. And by persist, I mean not that the same pattern that you detect in the tiling at some stage is exactly going from one time step to the other, but that the similar pattern, the computational version, the algorithmic version of this pattern is persistent in time. So there may be different types of such patterns, and people who have played with the game of life are acquainted with this idea. But some of them are special in the sense that they are interactive model builders, and this motivates this persistence in an algorithmic soup. Motivates the idea of agent. So here, agent or life refers to algorithmic patterns that readily interact but persist by capturing some structure of the world they inhabit to stay. By stay, I use the words homeostasis and telehomeostasis. Homeostasis, I'm sure you know what that means. It's just the finding the means to preserving the organism or the algorithmic pattern through computation or through time. And telehomeostasis, which is actually the more important goal, is to maintain the pattern throughout time. So even if it's not you, perhaps your children or your kin will be able to continue appearing in the evolution of the algorithmic system. And such patterns we call agents. So this is an important definition in the theory, not only because it tries to encapsulate what we think about agent and life, but also because it's provides the connection with the first person worldview. So in KT, the first person worldview is generalized by the definition of life. So life or agents of this type are what are capable of valence structure experience. So life or agents, as defined in this kind of algorithmic way, are what are capable of the first-person experience that we enjoy. Of course, as part of the program, we should study the algorithmic emergence of agents and life in digital systems, and this is an active field of research. Now, what agent elements are necessary? So, if we're trying to think about these interacting self-preserving systems, what should they have? So I would like to argue that they must have at least three parts. So, well, they have several elements: a membrane that separates them from the world. They have input and output channels with the world. Remember, here we're all in the algorithmic realm, so all there is algorithms and information being exchanged. And then they have a modeling engine, which is responsible for creating and running models of the world. An objective function, which is actually the core of the agent, is this telehomeostasis goal, which in turn implies it needs homeostatic goals. And a planning system. So the combination of these three things is, I would argue, the minimally sufficient complexity to actually have such an algorithmic agent. In more detail, the modeling engine also has several parts which are important. One is the comparator, which is the one responsible for comparing model predictions through a simulator and comparing them with inputs from the world. So the agent makes plans, acts on the world reacts, and the outputs are run through the comparator and the model simulator to see if the model is up to date. If the model is up to date, there is no error and no update needed, but if there are errors, then an updater needs to keep updating the model. And now I want to remark here that the central task of the agent is not creating models of the world or having very realistic models of the world. It needs to have both a good modeling engine and planning engine in order to maximize the objective function, which is the one that is the core of the agent. Okay, so now let's discuss a bit, since I've used the word model and perhaps also the word compression and symmetry, I would like to try to tie these concepts and bring them to you under the umbrella of algorithmic information theory. So, as we said, agents need to model the world, and this is an idea that it's been proposed before in cybernetics. The good regulator theorem is one of them. A famous paper. I have just recently released an algorithmic version of this, and there are other related papers. But the idea is that agents, in order to survive, they need to model the world. What do we mean by a model? So, in the algorithmic framework, it's not too complicated. So, a model of the world is a program that is able to emulate the data that it receives from the world. So, and a short description is a good model. So the shorter the model, the better description, the more powerful the model is supposed to be. So the definition of a model of a dataset is simply a succinct program that generates or compresses the dataset. Once you're able to compress data, you can also expand the compressed and recover data, or generate data that is similar to the one in the sense that it belongs to the same model. So here we touch on an important algorithmic information theory concept, which is Kolmogorov complexity. This is a beautiful and very elegant idea, which is a proxy, is the algorithmic definition of information, and basically the information contained by a data object is simply the length of the shortest program able to generate this data set. And there is another important fact here, and that is that it has been shown that the Kolmogorov complexity of a data set is in general uncomputable. So it's akin to the halting problem in the sense that there is no algorithm that is able to compute this. Yet we can aspire, and agents in life and ourselves strive to construct more compressive models of data, even though we will have no guarantee that we can actually find the shortest one. Here's an example of what I'm talking about. So on the left, you have a data set which looks, well, I don't know how well you can see, but it's a bunch of numbers. And it looks very complex and random. And actually, from all points of view, according to Shannon information theory, it is random. But in fact, it's generated by a very short program, the program on the right, which is a few lines of code. And it's actually a few lines of code to generate pi, the number pi. And here we find something interesting in the sense that the data set itself appears incompressible. If I had removed the first 4 lines of this data set and given it to you, it would have been very hard. And only knowing the like mathematics, maybe you have guessed that this is pi, but in practice it's very, very hard to do, to actually find this program. And so this is the idea that something that has high entropy from the classical sense actually has very low algorithmic complexity. It's a very short program. And the other idea I want to convey is that what we are interested in the program is trying to understand what is the structure lurking in the data, and what is the structure, how can we characterize the program, what elements, and I try to give below an attempt to that, which is simply to give you the program causal graph. So the program causal graph captures something about the structure of the program, and this is a way I've thought about that could be useful to try to characterize programs, for example. It's a very naive attempt, but I hope I can convey the idea that we should try to find mathematical tools to study the complexity, the structure of programs. And here's another example of a program. In this case, the program is a neural network, and it has been trained to classify images of cats. So whenever it's presented the image of a cat, the network spits out, it's a cat. And what I want to make emphasis on is the idea that in order to do so, such a network needs to capture invariant features of the space of cats. So the space of cats, of images of cats, have structure which is common, and this somehow must be embedded in the neural network in order for it to work. So there is a group of transformation that is associated with morphing images of cats, and the neural network somehow has captured this. Has captured other things. For example, if I take an image of a cat and it's a good neural network, if I translate the image of the cat, of the same cat in the image, it should still be recognizing. Or if I rotate it, it should also be doing the same. Or if I do a 3D change perspective, it should be doing the same, even if it's the same cat. So it understands the space of symmetries of cat space, but also of space itself, translations and rotations and so on. So all these symmetries have to be captured by the neural network. Another interesting idea is to think of science as compression, and this is quite natural, I suppose. For physicists to think about what we're trying to do is to discover laws that capture as many phenomena as possible. So it's an act of compression. Maxwell's equations or general relativity or the Standard Model are examples of simple rules, procedures, equations that capture a lot of the phenomena out there. So it's a fantastic act of compression. But examples of compression in science are not only in physics. Here's one also in biology. And natural selection and evolution are really mathematical recipes for compression. So a lot of the variants and phenomena found in biology, in nature, can be explained and compressed by using the notions of the theory of evolution. And in fact, the same algorithms that are carrying out this act of compression and simplicity, descriptive simplicity of what's out there, you can actually use them, in fact, in computers to generate artificial life and to actually look for solutions in equations. So they're really mathematical notions. Another bit that I need to give you for what's coming is the idea of mutual algorithmic information. I suppose everybody's familiar with the idea of mutual information in the Shannon sense. But with the algorithmic viewpoint, we encounter a mutual algorithmic information. So the idea is that the mutual algorithmic information between two strings is the amount of shared code that they have. So mathematically, it's defined as the difference between the length of the shortest code for one string plus the length of the shortest code for the other string separately, minus the length of the shortest code when you concatenate the strings. And the idea is that if you concatenate the strings, the structure that is in one, if it tells you something about the structure in the other, you can use it. So this minus term will be smaller and you will get mutual information. And you can use these ideas to talk about things like the algorithmic regulator and life. So the idea here is that in life, when we talk about models in living beings, what we mean is that there is mutual algorithmic information between the structure of the living being or the dynamics and what's happening outside in the world. So there is mutual algorithmic information between the world and the agent, or in this case, it's called a regulator, following the path of the regulator theorem. And this falls in line with the idea of all the recent papers that are coming out, arguing that general agents must contain world models. And it's basically following the idea that in order to survive, to have homeostasis and telehomeostasis, you must know something about your environment. Now, so this is kind of one of the pillars, and in the same paper I argue that it also implies that the system must have an objective function that is trying to maximize, etc. But I want to emphasize here the idea that short models are important. Why not use long programs? And following the ideology in Occam's razor that one should not increase beyond the necessary the number of entities required to explain anything, so we're implicitly assuming that data is generated by some process first that has some structure, and that a good bias to have in looking for models is that the universe is simple, that there are simple rules out there generating data. And there are different ways to argue why this is a good reason. In algorithmic information theory, there is the notion of the Solomon of Prior, which is precisely this idea that short programs are favored over long programs to explain data. And also, of course, there are more down-to-earth arguments that have to do with natural selection and the fact that we are resource-bounded agents, so we can only coarse-grain and compress and compute in a limited way. The Solomon of Prior has as a backbone the idea that there is a random program generation out there. And here I have an analogy showing you two types of scenarios, one in which there are monkeys typing sonnets, and then one on the right, monkeys typing programs. And the idea is that while monkeys typing sonnets will they'll have a hard time ever writing a complete sonnet. The combinatorials are very much against them. Monkeys typing prefix-free programs, self-limiting programs, are very likely to find and type programs that produce fantastic structures. And this is in line with the ideas of computational equivalence of Wolfram. So this idea that there are random generating programs out there underlying data is one that sustains the search, the motivated search for simplicity. And it's summarized here, and there are some theorems that show under some conditions that basically using such a simplicity bias is a good idea, as practice demonstrates. And as I mentioned before, this is used in science, so we look for simple solutions. And the idea is that as we add more complexity to our models, we at first we do some rapid jump in compression. We're able to explain a lot of data by adding some complexity into our models, but it arrives at some point that we are not gaining that much anymore. And this is formally described by the Kolmogorov structure function, which is this plot of the total description length of a data set versus the model size complexity, and the fact that there is an optimal point. So there is an optimal point from finding a short program. So this gives some idea on how to look for short programs. Now, another topic that is related to all this is the topic of reductionism. So what can we actually learn by looking at data? So, and I will discuss also the fact that even if we have access to microscopic laws, if we have managed to discover some microscopic laws like we do in physics, we are still far from using them to actually derive macroscopic laws that are interesting for us. So, and of course there are limitations. I mean, even if we have access to computers, we are resource bounded. So even if we have the micro laws for some system and we're able to run simulations, we are going to have some resource limitations, and agents themselves, life is certainly resource bounded in memory and computational power and energy. But then there are more fundamental things going on there. So One of them is the weak computational barrier, which basically says that agents can simulate bounded finite state systems step by step. Even if agents can do this, and the system that you're trying to simulate is bounded, there is no shortcut to actually deduce something about the macro scale. You have to actually run the entire simulation in order to learn something. And this is the principle of computational irreducibility. There is a strong computational barrier that says that even so if you allow a system size to grow without bound, so these are no longer closed systems, but if you allow the system that you're trying to emulate to grow, then there are some questions about some questions about the macro state of the system, which are equivalent to the halting problem. So there are some macro questions that are formally not only in practice but formally undecidable. And then I would like to add an algorithmic barrier, which states that the following: even for bounded finite state systems, there is no general algorithm that can guarantee the discovery of significantly compressed macro level models, even if you have access to the macro rules and the coarse-grained data alone. So this barrier actually arises from the global uncomputability of Kolmogorov complexity and the structure function. So it's an even perhaps even deeper point that because of uncomputability of the Kolmogorov complexity, for even simple systems, the fact that you have micro rules and you want to do coarse graining to derive macro laws, you find this fundamental barrier that you cannot compress. So again, these are kind of negative, but we shouldn't see them as negative points. They are just very interesting and motivate other questions. But they are barriers for agents. But they are barriers. They are not insurmountable barriers, and they are just limitations. And agents can still seek compressive models, even if they know they cannot derive them from first principles, or even if they cannot actually find the shortest program behind things. So there are very nice epistemic points here. This motivates the definition for emergence in the context of algorithmic information theory and algorithmic agents. So emergence is defined as a phenomenon associated to agents, and it has to do with this fact that there are strong barriers to discovering macro laws from micro. So when an agent is managing macro state data, or is trying to coarse grain the world in order to discover some way to compress data, and it finds such a way, then we call this, so there's a sudden drop in the structure function. So as the agent adds more bits to the programs that it's running, which may involve coarse graining and other computations, it will find a jump down in complexity. So it's able to do compressive steps. And this is what I think we mean when we talk about emergence. When we see an emergent phenomenon, it's something that we can try to describe with simple rules, but it's underivable in principle, even from first principles. Okay, now let me shift to the idea of, again, going back to models. How do we characterize models? So this question that I posed before. How can we detect and characterize these Platonic forms? So the intuition is that a model is an invariant of the data set. So the CAD model is the invariant property, the invariant structure of any CAD image. The CAD model, again, here is a program. So in a recent paper, we define models. We instantiated these programs using group theory, capturing the idea of simplicity as symmetry. And I think these ideas are very much connected. It's not just an artifact, but symmetry and simplicity and compression are very much related. So the idea is the following. We start with the definition of a generative model, which is a mapping from some configuration space into some higher dimensional space. Think of the latent space of an autoencoder. This could be the configuration space, and the unpacked part that generates your cat image or whatever is the high dimensional object. A Lie generative model is a model in which one can find a pseudo Lie group that acts on some reference image, and then by moving around in this latent space underlying the image space is able to generate objects there. And the idea is that there exist finite dimensional Lie pseudogroups. There are not Lie groups because they can only be defined in patches, most likely. But this is the idea. So it's a connection between compression or generation and Lie groups. And the intuition is that there is a connection thanks to the ideas of recursion and compositionality, which appear definitely in programming. These are the core properties of programs, recursion and compositionality. But they also appear in Lie groups, so you can do the same operation many times in order to construct a group element, but you can also combine them and compose them. So, and in fact, this technology of Lie groups has been used, for example, in robotics to describe the motion of robots. For example, here you have an image of hands. You can imagine them as robotic hands. And the motion and different shapes that this hand can take can be controlled with a Lie group that acts on the joints of the robot model. So Lie groups give us a handle on navigating the latent space underlying a generative model that is compressing data. And this is what this picture shows. You have the Lie pseudogroup, which is acting locally in some configuration space, and this maps out into the high dimensional space of, in this case, cat images, or you can imagine other things like the hand example that I gave before. So this is the first step, to associate generation of data and compression with Lie groups. And one of the assumptions is that the data out there in the world is generated in such a way. So we know it has symmetries and invariances, and one mathematical language to talk about that is that of Lie pseudogroups. Now, when an agent is tracking data, and as you remember, the agent is receiving data from the world and is trying to make predictions with its modeling system and matching data and predictions. So when it's successfully doing this, we can ask what are the implications of this. And one way to do that is to think, to describe the agent as an ordinary differential equation system, which can be very nonlinear, and you can think of it as a neural network, for example, if you wish. And the fact is that when it's tracking world data, there has to be a map out from the system variables into that which is being tracked. In this case, it would be the image, images of the moving hand that the robot is seeing are being tracked by the dynamics of the system through some mapping. So this is an interesting type of differential equation because it has a constraint. So it has a set of constraints. Now, the fact that this successful agent is tracking a hand has dynamical implications and it has structural implications. The structural implication is that if this hand is being manipulated and generated, this moving hand, by the action of a Lie group, then the structure of the differential equation has to respect invariances, the symmetries of the Lie group. So this gives you a set of equations that, for example, in the case of a neural network, that the weights need to satisfy. So, for example, if and this is already known, that if a neural network is to be invariant under rotations and translations of images of objects in an image, then the weights of this network need to satisfy some conditions. This is a generalization of this idea beyond translations and rotations by claiming that, for example, everything can be generated through Lie pseudogroups, and everything that is said to be invariant and to be some kind of object needs to have these invariances described by Lie pseudogroups. The second implication is that these constraints are conservation laws, and using Nether theorem-like arguments, one can deduce that the dynamics are reduced. So even though this system can be very highly dimensional, in fact, the dynamics collapse into reduced manifolds, and this has to do with the so-called manifold hypothesis, which refers to the fact that natural data seems to naturally collapse into reduced manifolds of much lower dimension than the embedding space. Here's a picture of this. So we have images of cat, which are, or the world of catness, of the world of cats out there, which is controlled by a Lie pseudogroup. This implies that the network that is successfully tracking these images, the agent that is tracking these images successfully and predicting, has to have some constraint, and it has to have some conservation laws and some reduced manifolds that become kind of the attractors of the dynamics when the agent is doing this task. So this is kind of joining these ideas, and the summary is that we can define generative models using group theory, and I offer one way to do this. I think it's fairly general, but there may be needed some more generalization beyond Lie pseudogroup into some looser objects. But the fact that systems are tracking this Lie-generated, this group-generated data with symmetries implies that they have to have structural constraints, and that because of this, dynamics collapse to manifolds. And since the constraints are hierarchical, and because natural data is compositional, you have these hierarchical manifolds, reduced manifolds. Okay, so let me pass to the next part of the talk, which is how we try to relate this agent, algorithmic formalism, and these Lie groups and dynamical systems theory into experience. So the central hypothesis here is that an agent has structure experience to the extent it's able to access encompassing and compressive models of the world. In other words, the models that these agents are able to create and run are the ones that embed, they endow with structure into our experience. So there's an isomorphism between first-person experience, structure, and the structure of the models that the agents run. So this is kind of a modern version of, here you have Schopenhauer saying the world is my representation, and we have Kolmogorov saying the world is a compressive program. I mean, this is an age-generated image, as you may imagine. They didn't live at the same time. So compression is at the core of cognition and life. World models, representations are all formalized by algorithmic information theory and Kolmogorov complexity, the idea of these short programs that capture structure. And life, which are here defined from the idea of algorithmic agent, crucially relies on compression. In order to visualize this, I like to provide this picture here in which I show these reduced manifolds, ideas for reduced manifolds abstractly. I mean, on the right you have some real attractors from simple dynamical systems. On the left, I give you an imagined one for what the dynamics of the brain of a person in some particular experience moment is manifesting. And the idea is that this correlation between the structure of these objects, the geometric properties, topological properties, and the structure experience. This is summarized here. So you have model structure, which manifests in structural constraints and dynamics, and the connection with structure experience. So this is a little bit the connection between algorithmic information theory, the algorithmic agent, and structure experience. And so the central element is structure. The central idea is structure is mathematics. But we can discuss it talking about algorithms, compositionality, complexity, and recursion, or we can talk about it in terms of dynamics, talking about complexity again, symmetry and stability, topology and geometry. And this structure also connects with the experiential part, the first person experience elements. And okay, and well, it's important also to emphasize that we have the concept of report, which is crucial in consciousness science. And I think we must always keep it in mind that it's important to remember that we are very limited to what we can access in terms of first-person experience. There are many systems which do not report and which may be sentient. So basically, in KT, an algorithmic report is a slice of its model. So it's a projection of the model that is running at the same time. This can be conveyed through writing, verbally, to oneself, to others. It can manifest as art as well. And this is what we can actually communicate to other sentient beings and to ourselves. And in the absence of it, we must remain agnostic about whether there is experience or not. Of course, in the theory, there's experience everywhere. Everything is experience. So, but I think algorithmic report and the need for having algorithmic reports is one of the clues to why some things appear to be conscious and some others not. In no report does not imply no experience. So we're getting close now to the end. We have talked about the structure of the world, but now I want to talk about algorithmic emotion and how agents may enjoy structure experience beyond just structure of the world, but also valence and arousal. And the basic idea is that the agent has these three modules: the modeling engine, the planning engine, and the objective function. And these ones, the mathematical characteristics of these modules are what create really the full, all the dimensions of structure experience. So they include the modeling, or the world model, self-model part. They include the valence, which is the value of the objective function. And in the theory, for now, this is considered a scalar. It's positive or negative, and that's it. And there's a planning, the structure of the planning system. And the three things provide the structure for the agent, and they actually map into the structure of experience. And we can follow this point of view to talk about neuropsychiatric disorders. So, for example, we can talk about an agent being depressed by stating that it's in a pathological state of persistent low valence. And we may ask, well, what could lead to an agent to have such an emotion? Why would an agent be stuck in a route of low valence? And there are different ways to arrive at this point. It could be that the modeling engine is not working well and it's providing the wrong models to the objective function that evaluates a low valence, or it could be that the objective function itself is in the agent is not functioning well and it's producing low valence. It could be that the planning engine is making the wrong plans, sending inputs to the world that impinge back on it and leading to further low valence. This is like a cognitive, both of these two are a kind of a cognitive profile of depression. It could be that the world itself is really a bad place to be, and that it's what is generating low valence in the agent. So this is kind of an algorithmic version of depression, and it gives you ideas on how depression may happen in human brains if you have a model of how to map this agent model into a human brain. And we try to do that in a recent paper, trying to assign the roles of modeling engine, including the comparator and the simulator, the objective function and the planning engine into the human brain. And this is a picture of what we propose. There are some parts of the brain that are specialized in modeling the world, parts which are more specialized in planning, and parts which are basically tasked with the evaluation of valence. And if this was a first draft of this attempt, of course, being able to do that would be very useful, because right now we are trying to develop computational models of the brain. We're trying to create mathematical models, mechanistic mathematical models of how the brain works, and we're trying to personalize these models to patients from their data. This is a process of data assimilation similar to weather forecasting. And even though this may be a very useful thing to do in neurology, for example, in epilepsy, we're running clinical studies now using such a computational modeling approach. We are a bit more stuck in neuropsychiatry. So, for example, in the case of depression, even if I have a perfect model of somebody's brain, down to unthinkable models of detail today, if I don't have something more, I am not going to be able to diagnose the problem easily. Because if I don't have a notion of how emotion maps into biology, and since depression is an experiential disorder, I will be stuck. So the idea is that with the agent model, if it's validated, then we can, if we can map the different modules of the agent into the brain, then we can really start asking questions about first-person experience, because the idea is that the agent model gives you a connection with the notion of first-person experience, structure, valence, etc. So the agent model, which is kind of a very abstract endeavor, we're actually using it to try to build better computational models and to interpret them. And in my particular case, the main driver of this is to develop brain stimulation solutions for patients in depression or other neuropsychiatric disorders. So we may say that we are now at this stage in computational neuroscience. If I may say a bit more about that, we're at the level of emulation. We're trying to emulate data so we have data from fMRI, we have data from EEG, from implanted electrodes, etc. And we are trying to build these mechanistic dynamical systems, which we call whole brain models, in order to emulate this well. And this is a very, very positive, significant step. But it cannot be the whole thing, right? I mean, the next level, I think, the next aspiration would be to imitate. So to not only reproduce data from neuroimaging, but also behavioral data, cognitive data. So this would be the idea of developing synthetic AI, so computational models that are actually able to carry out cognitive tasks. So not only emulating well neuroimaging data, but actually carrying tasks. I imagine someday being able to talk to one of these computational models, or neurotwins as we call them. But the final level will be to actually have these computational systems be able to produce neuroimaging data, emulate, to do what these systems do, and to feel what the human that is involved, is being mapped, feels. And this can be actually, as a view for the connecting first-person experience with science. This could be done perhaps on your own. So this would be a way to develop first-person science. It would be to make predictions based on your computational neurotwin system, that if you do such and such intervention, you should be feeling such a thing, or you should be seeing such a thing, or you could be imagining such a concept. So this technology, I think, is crucial for not only for neuropsychiatric disorders, but also for brain-to-computer or brain-to-brain interfaces. Anyways, the last part of the talk is about time. So I want to tell you about how these ideas connect with time, because I think it's very interesting. And this is very much inspired on work by Giulio and Barbour, who wrote this wonderful book some years ago about the end of time, and who I had the pleasure of meeting. So the idea here is that time is a construct. He calls it time is a great simplifier. And I push this idea forward a little bit using the algorithmic viewpoint and more of complexity, of course. But let's imagine the following thought experiment. We start from data generated from in the world or through a simulation. It doesn't matter. Imagine three particles flying in space in straight lines. So now imagine a system that's taking snapshots, but only producing them as a time series the distances between the different particles. So there are three particles, so there are three distances to keep track of, three rows in a data file. And we can also imagine that this camera or this system that is capturing this information is doing so erratically. So it's not really a good clock that is driving the camera. So you end up with a data set, which can be a huge data set. Let's imagine that this is done at length. And then we can carry out a sort of experiment of compressing this data set. So we feed all this data into some gigantic computer, and it's gonna try to find the simplest, the most compressed version of this. And what it will produce, if it's successful, it will rediscover Newton's laws. It will say the particles were flying in straight lines in something that we may call space and time. There is no space or time in the data file that I fed the system, but the computer will come up with these notions because it will allow it to simplify a lot the equations. Okay, so this is a bit of a cartoon image, but the basic point that Julian Barrow was making is that all the physics, the classical mechanics laws that we have derived are basically inventing space and time along in order to carry out this compression. We can also ask, along this same algorithmic view, what makes a good clock a good clock? So the idea is that a clock that we would call a good clock is one that when you use it, for example, to sequence, to capture the position of these free flying particles in space, along with its ticks, it's going to produce the simplest possible equation, which is a straight line. A bad clock, if it's running erratically or if it's speeding up or something, is going to give you a curve which is much more complex. So again, here is the idea that time is a simplifier. We construct Newtonian time and space because it allows us to simplify the equations. And this is part of the structure experience of the agent that we have built. Now, talking about where time comes from, and going back to the idea that it's somehow in the tiling, here's a picture that I try to represent the idea that there is a logical tiling, and embedded on it there's the idea of time slices of time, in which there is a lot of structure with mutual information between itself, and we can imagine that in this slice there are galaxies and there are agents, and in the agents' brains there are images of their recent past, and so on and so forth. And this is what Julian proposes as what really the universe is you have this Platonic space, which is kind of a 4D space, let's say in this case, and you have temporal slices in which you have structures like agents which contain and which observe around them or have observed and have snapshots of it in their memory streams of things that have happened in the past. And the structure in these slices is really what endows, which implicitly implies the idea of time. So this is the Barbour's Platonia, and the idea for why he says time doesn't exist is just an inference, and in which with which I agree from the algorithmic point of view and from the point of view of structure experience. Now we can play a little bit more with this idea. So let's ask, can we make an explanation for the idea that the subjective flow of time is different in different conditions? For example, if you're at the dentist and you're doing an intervention like a root canal, every minute that you are in there, it's feels like an hour or a day or a year, I suppose, depends on the. So there's a dilation of time, perception of time. And from the agent point of view, I would like to argue that when this happens is because when the system, the agent objective function is reporting low valence, the planning engine, it's running a lot of computations and simulations to try to figure out how to get out of that low valence state. So a painful low valence state is associated with slow passage of time because there are many cycles of CPU, many model calls, as opposed to when you're relaxed and you have fewer model calls because there is nothing that is really stressing the system. Similarly, we can apply this idea to the subjective flow of time as we age. So when I was a kid, I remember that, for example, when summer started, I had it looked like an infinite landscape there that I really was not even concerned what happened afterwards because it would flow so slowly. And now, as I've gotten older, in addition to the fact that summers are objectively shorter because of work, but also time seems to fly faster. Here, the idea is similar to the previous one, but instead of having updates on the model because of planning engine and objective function, which is stressing out the system, the idea is that when you're younger, you're learning a lot. There are a lot of model updates. And these model updates, again, is what one could objectively associate with a slower passage of time. And as we get older, there are fewer model updates, and there is less subjective flow of time. And now, in closing, algorithmic ethics and values, I want to emphasize that this framework does not grant any special status to humans, as you may imagine. All agents in this framework would enjoy structured experience, including pleasure and pain and valence. And this has ethical implications. Just a note here that this includes agents made of agents. So our cells are made of agents, our cells are agents, and we are made of agents. So it's fascinating how these hierarchical layers of agenthood rise, and perhaps societies, in some cases, or in some social animals, can be thought of as agents themselves. But the point is that agenthood carries by necessity pleasure and pain, and this motivates the idea of trying to develop some concept of algorithmic ethics. And, for example, defining what is good or evil. And we may come up with some ideas. This is just a sketch of some ideas, but for example, an agent A may be said to be circumstantially evil to agent B if its objective function increases when that of B decreases, but A does not contain that information in its world model, so it's unaware of it. Agent A is indifferently evil to agent B if its objective function increases when the objective function of B decreases, and A is aware of it, but it's not really too focused on that. It just happens to be that way. On the other hand, we may say that an agent A is intentionally or truly evil to another agent if its objective function increases when that of the simulation of B decreases. So agent A is actively trying to decrease the objective function of B. And similarly, you can apply this idea to being kind. And anyways, I think these are interesting things to talk about, and there are many interesting ethical implications. Of course, you have to, this worldview that I portray to you cannot be proven to some extent. I mean, it just seems like a cogent, rational, compact, compressed version of what I have experienced so far. So this brings me to the close, just to remind you the path that we did. We started from structured experience. We concluded there is mathematics, the science of structure and pure experience, and this leads to this view that we have the unicum, which is experience and mathematics as the backbone of everything. The rest is illusion. We talk about time, computation, models, symmetry, dynamics, and how they all connect with structured experience in the agent. And then finally, back to Greece. So Pythagoras, I would say, it's very closely associated with this worldview. Plato as well, even though he distanced himself a bit from the idea that the universe is actually numbers. He talked more about forms, but he also tried to bridge with other aspects of experience. Plutarch, I think, summarized something that is close to the agent model by saying that the soul and the psyche is immortal and tripartite, composed of three elements: reason, which is this blue part here, modeling engine and planning would be reason; spirit, thumos, which is experience; and appetite. Appetite is the objective function in the agent model. So as you can see, similar ideas with a bit more mathematical structure in them. And if you're interested in mathematics, I invite you to take a look at this special entropy issue that is still alive for the next few months, which is the mathematics of structure experience, exploring dynamics, topology, and complexity in the brain. And the idea is to try to develop these ideas further, trying to characterize compressive world models in a better way. How can we characterize models that AI systems derive or that are embedded in human brains? Mapping models to dynamical systems, empirical paradigms, and also looking at AI. So both computational brain modeling, but also AI and neurosynthetic AI. And finally, just to let you know that I'm happy to announce that we just founded a new foundation in Barcelona to really take these ideas further, to think about this some more. It's called the Barcelona Computational Foundation. And the foundation's aims are, it's a visionary nonprofit research foundation dedicated to understanding and recreating life, brains, and consciousness or mind as computational phenomena. The mission, the central mission is to advance computational neuropsychiatry and neurophenomenology, pioneer neurosynthetic AI, and ultimately providing the means for better lives and societies. May this be biological, hybrid, or synthetic ones. To achieve the mission, we need a framework capable of spanning multiple disciplines, as you can imagine, and spanning from the micro to macro scales, from philosophy to algorithmic information theory, physics, life, neuroscience, and social sciences. And the idea is to try to move forward these computational principles to across science, and also to bridge the objective with the subjective. So these two aspects of the problem. So this is an initiative that I did with Francesca. Francesca Castaldo is the co-founder. And also the other members of the foundation are Gustavo Deco, a famous computational neuroscientist and a good friend, and Ricard Solé, a biologist and physicist and expert in complex systems, and as head of the Science Advisory Board, Carl Freestone. And I'm also happy to report that we have in the Science Advisory Board other important people, including Michael, who agreed to support our Science Advisory Board. And with that, I would like to close and thank you all for your attention. If you're interested in the slides, you can find them at this QR code. Thank you very much.